Thank you.
Thank you.
So once again, hello everyone. My name is Álvaro González. I'm a Colombian PhD student working in Moscow in Skoltech. And today I want to talk to you about how to price energy in integrated heat and power markets. And let's start talking a bit about what is an integrated heat and power market. So basically, this is when we have okay, now I can see. Okay, when we have an integrated heat and power system, we talk about a system that has electricity generation and consumption, but we also have heat generation and consumption. And usually we treat them in the engineering practice as two independent systems, but they are in reality already linked by physical devices such as cogeneration plants and heat pumps, and also by the way in which their primary energy is supplied through the gas network, for instance. So why do we want to combine these two systems in the operation of these two systems is because in this manner, if we co-optimize how they operate, we can actually increase the fuel efficiency, taking advantage of the redundancies of supply that we have in the system, and also how the demand profiles correlate with one another. Also, adding the operation of the heating system would allow us to provide a better balancing response for renewable resources, because if we have an overproduction of renewable generation, we can actually transform that extra electricity into local heat that would allow us to balance the system in a better way. And the interaction between these two systems have been gaining more and more attention. And this has led to go from the operational questions and technical questions to a market perspective that is what allows it to be actually implemented in reality. So for this, we present here, let's say, the basic formulation for how an integrated heat and power market would work. So if we have electric consumer bits shown here in blue with the B, and we have the same from the heating users here in red, we would try to maximize the social welfare in our combined system by maximizing the utility of our users minus the generation cost of the systems that we can normally represent with a quadratic cost function based on how much power and heat is generated by each one of our units. In order to be a proper market, we need to have a demand balance. So in this case, we will have two types of balances, one for electricity and one for heat. And we need to model how the generation units are going to operate. And for this, we can use, let's say, a combination of inequalities to define the operating region of our unit. So think of this as the generation limits that you usually see in a electricity only generation unit. So you have a minimum energy that is possible to be generated and maximum capacity. And finally, we can assume that our demand for electricity and for heat has certain limits, so it can move within a range, so we have some flexibility in our demand. So this demand is not inelastic. Okay, so how do we actually represent the different types of generation units? Because we have some units that produce only electricity, some that produce only heat, and some that can actually generate both. So for this, we use the inequality that is shown here, and depending on the value of these coefficients K, they can actually, let's say, represent a different thing. So for instance, if we have an electricity only unit, we wouldn't have the coefficient KH because it's not producing heat, and then the limits would change accordingly with how big the coefficients are. And this is the general shape that a generation unit in such a system could have. And here we have all the possible physical combinations that can appear in such a system. So for instance, an electric generator can be operating only along the bound number 2, so the line here, and a gas boiler would operate around the bound number 4. But for cogeneration units, depending on how we change the coefficient case, as we have here in this table, then it's going to have different bounds depending on their sign, and also in the magnitude is going to increase or decrease the operation range of the unit. And since we're talking about markets, our interest is of finding the energy prices. So if we apply duality theory to this really simple linear problem, we can see that the electricity price, represented here with lambda, can be calculated as the marginal generation price of the generator, of the electric generator, plus a compilation of what is happening with this constraint that we have here, this generation constraint. And the value of mu is the dual variable associated with that constraint, and its value is different than 0, is greater than 0, when this constraint is binding. So that means that when a generator is operating along any of these boundary lines, then the value of mu is greater than 0. Now, if the value of k is greater than 0 also, of the associated k is greater than 0, then that means that the electricity price is going to be higher than the marginal generation cost. So the generator is going to turn in a profit. But if this value is equal to 0, then we have that the electricity price matches the marginal generation cost, so there is no profit. However, if this coefficient k is lower than 0, then the electricity price is going to be lower than the marginal generation cost. And that means that that generator is not going to be recovering the generation cost when it's paid at the closing of the market. And we can evidence that in this table that shows us basically along each one of the boundary lines, we're going to have a different relationship between the electricity and heating prices with the respective marginal generation cost. So depending on the point where our generator is at the end operating, then we are going to have basically a possibility of not being able to recover the generation costs. So what we propose is to create a really simple model that takes the dispatch demand and the dispatch generation from the previous problem, and is going to return us some charges and payments that are going to be coming from users and generators to finally give us an adjusted energy price for electricity and for heat that is going to allow to all of the generators to recover their generation costs. And the objective of this model is to minimize the payments that are being done or that are being given to our different users and generators. And we do this in the following way. First, we define a budget balance. So that means that the payments and charges done to generators and users have to be equal to 0. So they need to cancel each other out. In this case, there is no missing money, and we don't need to do then some extra uplifts that are external from the market. We have to model the utility of our users because now we have a new electricity price and heating price, and we have new uplifts and charges. So the user's utility must be recalculated, and the same happens with the generator's profit. And at the end, we want that the profit of the generators and the utility of the users have to be greater than 0, greater or equal than 0. That means that there is no loss for the generators in this type of a scheme. And at the end, we end up with a simple linear programming problem that can be modified and amplified to take into account the time constraints or network constraints and additional market properties that we would want to have. So for instance, monotonicity in the price charges and so on. Okay, so to test our model, we created two scenarios. The first one is presented here as the summary scenario. So in this case, we have two electricity users shown as D and two heating users shown as Q. And we have two cogeneration units. And when we make the dispatch, we have the following result, that generator 1 is producing heat and electricity, and generator 2 is only producing electricity since it's along the vertical line. If we analyze the surplus and the profit that we have for users and generators, we can see that the generator 1 does not recover the marginal generation cost for electricity and for heat, since it is along this boundary line, and we can track that down to the previous slides. So we can see this graphically here, where we see that the electricity price has been set below the marginal generation cost of generator 1. So that's why we have this orange area that says NR, so not recovered cost. And that means that we need to find a new price that we implemented the second model, and we have a new price. However, this price now matches the bid made from demand number 1, but is higher than the bid made from demand number 2. So demand number 2 has no more money to pay at this new price. And then this is also below the marginal generation cost that we had for the generation 1. So what must be done? Then we charge generator 2 from its extra profit, because now we have a higher price, and we can charge this generator some amount of money to cover the uplifts that we need to do for the demand and the other generator. In the heating system, we have a similar situation, so we must raise our price gamma for heat. But in this case, when we raise it, now it matches the generation cost for this unit, but we don't need to do any uplift of charges because it is below the bids of the heating user, so everything is fine at this new price. Now for the winter scenario, we have a similar situation, but we increase the heating demand of our users. And as we can see here, now both generators are producing heat and electricity. In this case, we're going to have that since they are along the same boundary line, neither of the generators is going to recover the marginal generation cost for electricity. So we can see it here directly in this figure. So all this orange area is not recovered cost. So once again, we run our proposed methodology, and the new price is going to actually match the bid from demand number 1. But once again, we need to make some uplift payments for demand number 2 and generator 1 that comes from the extra profit that is being taken by generator 2. In the heating system, however, now the energy price is higher than the marginal generation cost for any of the generators, so we have no need to recalculate the price, and this is a result also from the optimization model. To conclude, we have seen that there is an increase in the interest of making integrated heat and power systems, and even integrating the gas networks into it, to create markets that would provide flexibility to our power system, and also to reduce the cost. However, in these markets and in the current methodology that is being employed by the majority of the papers, there is no guarantee of cost recovery for the generators. So that's why we presented a simple linear programming problem that can be done after the main dispatch that would allow to guarantee the cost recovery for the generators, and then this incentivize that this market is actually being participated by the different generators that we have, because they are sure that they're going to recover the cost. We also have that we ensure cost recovery per energy vector, so we ensure cost recovery for electricity and for heat separated. So that means that there is no gonna be cross subsidy between the users, so the heating users are not gonna subsidize electricity users and vice versa, because they are considered in a separate manner. And finally, this simple model that we presented here can be expanded to take into account all types of market properties and time and temporal and spatial constraints. So thank you for your attention. If you have any questions, please.
Thank you very much, Alvaro. Any questions? We are a bit past our time. No questions. Thank you. Let's answer it. Thank you for the excellent presentation. When charging G2, the difference between marginal price and cost will reduce its fixed cost remuneration from market mechanism. Also, can this marginal price correction be incorporated directly to the optimization problem?
Charging G2, the difference between
when, yeah.
Yeah, I can read it here again. Yeah.
Okay.
Okay. So yes, we reduce the remuneration that we have here, but for instance, in this case here, but we need to take into account that this remuneration was extra. It was unexpected. So in this case, the actual remuneration that they would have taken this generator to would have been negative, as we see here in the figure with the orange. And now the remuneration that it's going to get is zero. So it's going to match the generation cost. So in this case, we're not inflicting any damage into that generator. We're just making everything, let's say, not so bad for him. And the second part of the question is, if the price can be included in the main optimization problem. Well, the problem is that these prices come from the dual of the optimization problem. So that means that we would have to add the complementarity constraints in the primal problem, that is the dispatch. And in this case, we would have a nonlinear term there, a bilinear term. So this multiplication of variables is going to make our problem non-convex. So that's why we do it in a two-step manner. But the results of the dispatch are the same. The only thing that changes are the prices.
Okay, thank you very much, Alvaro.